Hey guys, so today we're going to be talking about complexity analysis using big O notation. Now, big O notation might be something that you may have heard of before, or maybe this is your first time hearing of it. Don't worry, by the end of this lecture, you should understand what big O notation is and how to use it to analyze your code. All right, let's begin. So some of you may have seen the slide before as I've used it in a past lecture, but just to go over it again, we've talked about the goals of the software developer. One being to solve a problem at hand, but also you need to solve a problem well. And then we talked about different ways that you might go about it, and I broke it down into three different buckets. One being structurally, where we talked about proper data structure usage using classes, proper architecture, but also simple things like commenting your code using proper named variables, adhering to coding standards, and many other developer-oriented optimizations there. We also talked about functionally. This is more geared towards your end user. Basically, what features do you offer to your end user through your software solution? Also, how intuitive it is. We talked about UI, UX design, which is a huge component of functionally improving your code. But the final bucket that we touched upon was algorithmically. And that's actually going to be the focal point of this lecture. So let's talk about it further. So when we talk about improving your code algorithmically, we usually focus on two key factors. One is execution speed optimizations. So this is where we're trying to improve how quickly our algorithm can complete a task. And then secondly, we often focus on resource optimizations. And here it's often memory. How much memory is your algorithm using? And if you can improve that through optimizations. So yeah, speed and memory are the two main resources that we're trying to optimize. But usually even talking about those two, speed is usually the main focal point. So memory can be an issue, especially if you're developing resource intensive applications like a video editing software or data analytical tools, that those can take a lot of memory. However, in most cases, speed is the main thing that we're trying to improve with our solutions. So throughout this lecture, I'm probably talking about speed, but again, all these topics can also relate to memory optimizations as well. All right. So the key thing is this lecture is not actually going to be focusing on how you can improve your algorithms, but more about how to detect and analyze your algorithms and then identify what can be improved from that point on. All right, so that's a key distinction I want to make before we get into it. But now that we could talk about big O notation. So a question you guys might definitely have right now is, what is big O notation? We can describe it as a way to represent the relative complexity of a given algorithm. So I guess stating it another way, we can use it to describe how an algorithm's performance is impacted by a change in the size of inputs. So for example, if your data size increases tenfold, how does your algorithm react? Does its execution time remain the same? Does it increase tenfold? Does it increase 100-fold? These are key factors of analyzing how your application might behave. So when you see big O notation, you often will see it, a big O, and then in parentheses, you'll see some factor, whether it be n, might be a number, might be, like a formula in there. So just an example usage of terminology, you might hear something like, this algorithm has O of n time complexity and O of 1 memory complexity. So again, we'll get into what those terms actually mean, but just when you pronounce, when you see O parentheses n, we usually say O of n or O of 1 in these examples. So just get familiar with that terminology because you'll likely hear it once you get into the software field. All right. So again, talking more about big O notation, it's not the only type of notation that you might come across. It is probably the most common, but just to define big O notation further, it represents the worst case complexity for your algorithms. So this is, again, very important to developers because usually we want to know what's, in the worst cases, like if everything goes wrong with our algorithm, what's the maximum amount of time will it take? So that's what big O notation is used to kind of represent. But other notations that you guys might come across, one being big theta notation, and this represents your average case complexity. And finally, we have big omega notation, which represents your best case complexity. So just give like examples of these. Let's start with a simple example of like linear search through a list in Python. So for example, let's say you're searching for an item and it happens to be your very first item that you search is the item you're looking for. Well, in that case, that's your best case scenario. So your omega would actually be omega of 1, meaning that you found in your best circumstance, your algorithm will take constant time to find what it's looking for. Now, that's not usually too relevant because that's, again, in the ideal world, you might get lucky and just find your item right away. But usually we focus more on average case complexity and worst case complexity as developers. So big theta notation represents your average case. So in this case, if we're trying to find an item in a list and we're using linear search, our average case would be probably half the number of elements. So if we have 10 elements, on average, if we know an item exists in there, it'll probably take on average 5 searches to get through that array to find the item if it's in there. If it's not, then we're probably going to go through the array much more often. But that's where big theta notation becomes relevant. But as I said, big O notation is usually the most common that you talked about, and that's the worst case because usually we want to know, if everything goes wrong, what will be our time hit for this algorithm. So big O notation is a very popular interview question. That's again, this is a good reason to understand this material. It's not too relevant in terms of actual development, but for theory and kind of just understanding on a high level complexity of algorithms, big O notation is definitely a popular interview question that you might get asked. So hopefully this lecture will kind of prepare you for that. All right, so let's actually look at some big O notations and some common algorithmic complexities. So I have a few listed here. I just want to note that these aren't all the types. There's, I guess, infinite permutations theoretically, but these are the most common that you'll come across. So to start, you might see O of 1, and this is known as constant time complexity. And this just means that regardless of your input, your time complexity won't change. So we'll talk more about these in details, but just to kind of highlight them, we have logarithmic time. So that's notation O of log n. We also can have linear time, which is simply O of n. Then we have something called log linear time. This has a few different names, but this is n times log n. And then we also have n squared, which is quadratic time. And then we could even have something that's O of 2 of n. Again, this 2 can be anything, but in this case, we just use that for exponential time. All right, so just to I guess, be specific, we want to minimize time. So the larger our numbers, that's bad for our algorithms whenever we're talking about complexity for time. So in this case, O of 1 is your best. It's that means your algorithm's faster, relatively faster, compared to if you have an algorithm that is like quadratic time or exponential time, that means it's much, much slower. All right, so let's actually talk about some of these more in detail. Let's start with O of 1. So again, as I mentioned, this is constant time complexity. And this just means that your execution speed for your algorithm will not change regardless of the input data. All right, so a simple way to understand this might be if you think about appending an item to a list. All right, so let's say I give you a list and your task is simply to add on an item to the very end of it. Well, at that point, like the size of your initial list doesn't really matter, right? So if I hand you a list that has 10 elements in it, or maybe 1,000 elements in it, appending an item at the very end is a constant time operation, as in the data size does not impact how long it will take to append one item at the very end. All right, so constant time is the best where, again, your algorithm does not change regardless of how the data changes. All right, next we have logarithmic time complexity. So now this is where your execution speed, as you might guess, grows logarithmically based on your input size. And again, going back to maybe math class from high school, logarithms, if you remember the chart, this means it's a slow growth over time. So like, when you go from 100 to maybe 1,000 for your data size, like your increase in time is not going to be as much as your data is growing. All right, so this is a common complexity for divide and conquer algorithms where you're breaking a larger problem down into smaller and smaller bits. So one great example is binary search algorithm. This is one of the challenges we had in past weeks. So hopefully you guys are familiar with this algorithm. But yeah, so the time complexity for binary search will be described as log of n, or O of log n. All right, so next up we have linear time complexity. So the notation for this is O of n. And this just means your execution speed grows linearly or proportionally to your data size. So for example, if your data size grows tenfold, your algorithm, worst case, complexity will grow tenfold as well. And a simple example, again, another familiar algorithm that you guys have implemented is the linear search algorithm. So this is basically saying if I hand you an array that has 10 elements in it, your worst case will generally be having to inspect each element in that array being 10 elements. But if I give you an array of 100 elements, your worst case is that you got to go through 100 elements. So again, it scales proportionally based on the data size there. All right, next up we have log linear, also lin arithmetic time complexity. I've heard of other names also. This one, your speed grows log linearly. So that's basically n times log n. And I would describe that as quickly. So it does kind of accelerate with time, but with data size, but not dramatically. One great example for that is the merge sort algorithm. If you're familiar with that one, that has n log n time complexity. All right. Next up, we have quadratic time complexity. Notation for this is O of n squared. So this just means that your speed grows quadratically, i.e. very quickly based on your input size. So this is the case where if your data size grows by 10, your algorithmic worst time complexity will grow by a factor of 100. So again, you could probably see that this can get out of hand if you have an algorithm that's n squared. The larger your data gets, the even longer and longer it'll take for your algorithm to finish computing whatever it's trying to compute. So one example we could talk about is finding duplicate values within a list. This can be quadratic time complexity. So we can take a look at that. So actually, let's actually look at some code because it might be kind of better to see it in action. So I have a few coding examples coded up here. So I have an array with various elements in it. It looks like maybe there's anywhere from 10 to 15 elements in here, just random numbers, not sorted. So an example of constant time complexity that we talked about is appending an item. So if I called append to list and passed in my data here, this will take constant time. Again, to reiterate, that just means no matter how many items I have in here, like I might just add, I keep adding as many as I want. That's not going to impact the performance of this function because this function is simply appending an item, and that's all it's doing. It does not, the size of the data does not impact the append operation. We're just tacking it on at the very end, regardless if there's 20 items, 200 items, 2 million items, we don't care. One append will take constant time. So that's an example of O of n. All right, let me delete these extra items. So let's label that as O of 1 is constant time. All right, so let's talk about an example of linear time complexity. So in this case, I have coded up a function that is basically finding a value that might be greater than the passed-in value. And it's going to go through my data and try to find something that's higher than the value that I passed into this function. If it finds something, it'll return the index, else it'll return none, as in it didn't find any item that was greater than the value that I specified. So in this case, this is linear time because at worst, again, in the worst case, we're going to go through every single item in our data and then check it to see if it's greater than our value. Again, this is worst case, but if we're talking about average case complexity or best case complexity, our values might be a little different because, for example, if we find a value halfway through, we don't have to actually go through all the elements, and that might be our average case. Or again, if the first item we check happens to be greater than the value we passed in, well, that'd be our best case time complexity. But again, as I mentioned before, for developers, best case usually isn't too meaningful. Average case is usually pretty important, but worst case is usually what we're focused on most of the time. All right, so this is an example of linear time complexity. So let's give that a notation. That's O of n. So that just means that if your value of your data size is n, your time is also going to grow by a factor of n. That's kind of the notation there. All right, so let's also talk about quadratic time complexity. So we have an example here. I have a function that's called find double. The job of this function is to take in data and see if there's any other elements in my data that is double one of the existing values. So basically, I'm going to loop through my data once and then compare it against all other values, and then do this multiplication where I check if one value is double the other. If I find something, I'll return true. That matches that case. If I go through my entire data and don't find any values that are double of another item, then I'll return false. So in this case, we have quadratic time complexity because not only are we going through our data one time, but we're nesting for loops here. So if we kind of think about this, we have our data, we grab our first item in it, and then we run another for loop. This for loop will go through all items potentially in the same data list, right? So I'm going to grab a D2 and then compare it, try doubling it and see if it's double my given value of D1. And then if that's not true, it's going to keep going through this for loop just for my very first value, D1 that I extract from my data. However, if I go through my entire for loop and don't find any value that's doubled, well, then I'm going to proceed in my outer for loop here and grab the second value in my data and assign that to D1 and then run this for loop potentially all over again. So if you can kind of math it out, I'm going to run this n amount of times. So let's say my data has 10 values in it. This outer for loop is going to run at most 10 times in my worst case. And then my inner for loop is going to run 10 times for each iteration of my outer loop. So if I do this 10 times, but each time for each of those elements, I do the inner for loop potentially 10 times, that's going to be 10 times 10 runs of the inner for loop. So that's going to be up to 100 iterations for this entire algorithm. All right, so my input size was a value of 10, I guess 10 items, and then the number of iterations was 100. So as you can see, that was quadratic. So yeah, if I take 10, square it, I'm going to get 100. And that's kind of why it's quadratic complexity. So I will give that a name of O of n squared. All right, so that's an example of quadratic time complexity. So usually algorithms that are designed in this manner are not very efficient. As we kind of talked about, if your input size grows by 10, your time complexity grows by 100. And that can get out of control, especially if your data gets much larger. So usually if you catch yourself writing nested for loops like I have here, you definitely want to be mindful of it. You might not be able to get away from it. Like if you have a task to do, you still have to do it. But there might be optimizations you can employ or even restructure your entire algorithm to avoid the quadratic time complexity. It usually comes down to a case-by-case basis. There's no magic formula that says, hey, I can break this up and make it like less than quadratic time complexity. All right, so the key takeaway is just be mindful when you're writing algorithms that are, I guess, higher level time complexity. Just be mindful of optimizations you can make or maybe restructuring if possible. All right, let's go back to my slides. One more that I want to talk about. We have exponential time complexity. So this is where your execution speed grows exponentially or ridiculously quickly based on your input size. So a great example is Fibonacci. This is actually another challenge that we've done in the past. So we can actually see an example of exponential time complexity and kind of see how quickly it gets out of hand. So I actually have Fibonacci coded up. So let me bring that up here. All right, so I've employed the Fibonacci algorithm using recursion. So as you can see, I'm calling my method again at the bottom to compute the values that I need to. All right, here I have a global variable called calls. That's just tracking how many times I'm actually calling Fibonacci. So I have the global variable. I increment it each one time, every time that I come into this function and compute something. All right, and then below, I kind of just set up an example here. So I have my n values that I could kind of change, and I'll print out my n value, the computed Fibonacci value, and also at the very end, will show how many calls I've made based on the value of n. So my input, I guess, size is n, and then my time complexity can be measured by the number of calls I'm making. All right, so let's give this a run and try a few examples and kind of see how many times I'm calling my Fibonacci function based on how my value of n changes. Let me bring up my terminal here. I'm going to run Python fib. All right, so for a very low value of n, I have n equals 2. My fib value is 1, and I only actually had to make one call to my Fibonacci function. So that's not too bad. but let's actually increase our n to 4. And let's see kind of how our calls gets impacted. So we can run that again. All right, so my n value is 4 and my calls made is 5. So, that seems, at this point, it seems kind of linear, right? Like when n equals 2, calls is 1. When n equals 4, calls is 5. So right now, I'm not too worried about it. Let's actually increase this to 6. I'm kind of just going by 2 right now. Let's run this again. All right, so definitely not linear anymore, right? So I increased to 6, and my calls made is now up to 15. So it's more than double what it is now. But when I had n equals 4, my calls was simply 5. So I'm definitely increasing by more steps than my input is. My input went up by a value of 2, but my calls made went up by, I guess, a value like multiple of 3. So kind of can see it accelerating, but let's go to let's go to 8 and kind of see what we get. Let's run that again. All right. So when I went to 8, my calls made jumped to 41. All right. Now I'm going to actually take steps by 1. So I'm going to increase to n equals 9. And let's run that again. Calls made jumps to 67. All right. Let's jump a little bit more. Let's go to 12 and see how long this takes. All right. So now I'm in the 200s. I'm up to almost 300 calls when my n equals a mere 12. Right. So you can kind of see that this is kind of accelerating way beyond what we might want it to. So if I actually double this, let's make it 24. Let's see how many calls that this algorithm needs to make. All right, so we doubled our input here. So we went from 12 to 24, so our size doubled. But look at what happened to our calls. We went from 287 to over 92,000 calls for when our factor doubled. Our input size doubled, our time value, I don't know, that's a factor of what, 300 maybe? So let's just do one more doubling and kind of call it quits for the day, because I think we kind of see what's going on here. Again, this is an example of exponential time complexity, meaning that as your input size grows, your time complexity is going to grow exponentially. And I think we're all kind of familiar with exponential. The concept of exponentials just means it's just running faster and faster and faster each time. All right, so I'm going to try n equals 48. I'm not even sure what this value is going to be. All right, so it's actually taking a decent amount of time. As you can see, I have no output still. I'm not even sure if this is going to complete in a reasonable amount of time, so I might have to abandon it. But let's give it maybe a few seconds. And yeah, so at this point, I'm just going to say it's spiraled out of control in terms of we're probably in the millions at this point. So I'm actually going to quit this and try something more reasonable. So let's go to 30. I think 30 should be a reasonable amount. So we can clear this and run this. All right, so I increased it to 30, and yeah, so for a value of 30, we're already in the millions. Right here we have 1.6 million, it looks like. So just imagine for 48, we're probably in the tens of millions, maybe hundreds of millions. And at that point, we're probably gonna be waiting here minutes, if not hours, for that to compute. But yeah, that's just a good example of exponential time complexity. The key takeaway here is don't have exponential algorithms. If you do, they're not gonna last very long for larger data inputs. All right, so that was Fibonacci, and that was O of 2n. So that's, again, that 2 is just kind of arbitrary. But the main takeaway is that we have an n exponent. So your execution speed is just going to be blown up, basically, as your data gets bigger and bigger. All right, again, so these are common BigO notations that you might come across, or I guess common time complexities. Hopefully you're not seeing exponential too often. But again, Fibonacci is one example of exponential time complexity. All right, so let's proceed. So I actually found this cool chart. This is from BigOcheatsheet.com. I have it listed down here. But this is a kind of neat chart that kind of shows the different types of time complexities and how they're impacted as your element size or your data size grows. So one thing to note here, that these scales, the operation scale and the element scale, are not equivalent, as in they're not both equal scales. So if you notice, we have O of n here. This is actually linear, like a linear graph. That's where x equals y. But notice that we're not kind of just slicing this in half. We're very narrow here. So again, this is not equally scaled. So that's something to keep in mind. But the reason this chart is not equally scaled is because they want to kind of highlight these algorithm complexities over here. So as you can see, we have O of n squared, which is not a very good complexity to have, because as your elements grows, it gets kind of out of control, right? We talked about exponential complexity. Again, that's even worse. Like it just goes pretty much straight up at this point, even though our scales are trying to fit these in there. One complexity that we did not talk about, but definitely can exist, is O of n factorial. Again, this is even worse than exponential complexity. One, I guess, typical algorithm that can be n factorial is when you're trying to list permutations from inputs. Like if you have an array with 10 elements, you want to know each and every combination that can be made from it. That likely will be a factorial complexity time operation. So yeah, so this chart's kind of divided into buckets. We have your horrible bucket, and so n factorial, exponential time complexity, and quadratic complexity are usually regarded as horrible, as in poor performing algorithms. So again, if you can avoid creating algorithms that fall into this bucket, you'll generally be happier because of it. Then we have this kind of like middle case. This is O n log of n. Again, this is the log linear algorithm complexity. And this one isn't too bad. As you can see, it kind of is growing over time, but it's not too bad. Again, it's definitely not in these buckets where it's kind of going like kind of exponential or straight up, and there's no sky's the limit there. But yeah, so then in the fair bucket, we have O of n. So this is the linear time complexity. That's regarded as, generally good. Usually, you're going to be writing for loops and going through your entire data. That's typically common. But then if you can implement solutions that are less than linear time complexity, such as log of n, again, binary search is a great candidate to talk about here, but that just improves upon linear time complexity. And then O of 1, that's the kind of the best you can get. That just means constant time, as in it's agnostic to the size of your data. Basically, your operation is going to take a flat amount of time each time, regardless of data size. So again, this is a pretty cool chart. Actually, just to rep BigO cheat sheet a bit more, I actually have it pulled up here. It's a great site. Again, if you're looking to learn more about time complexity, I would definitely kind of guide you to this. They have this great chart that I kind of borrowed, but they also go more in depth. They talk about different data structures. So it's something that we covered recently. We have like linked lists, stacks and queues, arrays, also like trees. So they also talk about what time complexity it takes to do various actions, such as searching for an item in an array compared to like a binary search tree. You can see the different time complexities there. Also like inserting items, deleting items. They talk about average time complexity, worst case. Again, that's the big O. Average is the theta, and we also have space complexity. So this is something that I didn't specifically talk about too much in detail, but this is like how much memory does do these data structures take up. All right, and then again, they have other algorithms they talk about, sorting algorithms, so you kind of compare and kind of see which ones fare better or fare worse in their average complexity versus their worst. So a lot to learn about here, so a great site to check out if you get a chance to. So that's bigocheatsheet.com. All right, so let's proceed. All right, so let's actually try to analyze some code. So I have some code snippets coded up, and I kind of want you guys to kind of look at the code and kind of see if you could determine what BigO notation you would attribute to the algorithms. All right, so let's go back to my coding window here. All right, so for our first example, I have a function called example1. Not very imaginative, I know, but let's talk about what's going on here. So I have a variable called dual sum. And the goal of this function is basically to go through my data and basically have a running total of summing up two individual elements for my data. So for example, if I have 10 elements, I want to add like the first element and the first element together, and then the first element and the second element together, and then take that sum and add it to the sum that I computed before. Just keep a running total for both elements that I am summing up. All right, so basically, again, I have dual sum. I'm appending or adding on x and y, where x and y are two various elements in my data. They may be the same element, they might be different elements. I just want to go through each combination that I can make for my data. All right, so if you can kind of look at this and think about it for a second, and then let's talk about what big O notation would you say this is for, again, the worst case runtime complexity. All right, so hopefully you had a moment to think about it. Let's actually talk about it. So a good telltale sign is usually looking at how many for loops do you have over your data range. So in this case, I'm passing my data, and I notice I have a for loop here, where I grab an x, assign an element to x. Then I have a nested for loop. So again, this is something we briefly talked about earlier, but when you have nested for loops, you're basically going to run the inner for loop as the inner for loop might run to completion X amount of times, where, sorry, not X, I should say the size of your data. So my outer for loop will grab a value, and then the inner for loop may run to completion, meaning it's going to go through my entire data once. But then I'm going to go back to my outer for loop and go to the next value and do the whole thing over again for my inner for loop. So again, this is going to be actually a quadratic time complexity. So that's O of n squared, because I'm actually looping over my data twice in nested for loop. All right, so the inner for loop is actually going to be run n squared times based on the size of my data, where n equals the size of my data. All right, so in this example, this would actually be O of n squared. Let me write that correctly, hopefully. N squared. All right, so hopefully you guys were able to get that one. Again, for loops are kind of a telltale sign of, if you have one for loop, that's going to be O of n. If you have a nested for loop in there, usually that's going to be O of n squared. Again, you want to make sure that you're factoring in the input for that computation. So as data changes, the time of this is going to change by a factor of n squared, where if my data changes by a value of n. All right, let's move on to another example. So here we have example 2. I have a function aptly named example 2. So this, this function is actually just trying to find if there's a duplicate item in my data. And this is actually going to, it's not going to self-match, for example. It's not going to match like the first element against the first element. So that's what the j not equals I. We're just making sure that indices we're comparing are not the same. And then here we're checking if we have matching data. If we do, we return true. If we don't, then we return false. So kind of look at this, and let's determine what big O notation we'd attribute to this algorithm. All right, so hopefully you guys had a moment to think about it. So here I'm looking at it, and I see that I have a for loop. That's going to tell me this is probably at least O of n. And then I look at this, and I don't see any other nested for loop. So that's going to lead me to believe that this is O of n. But is this actually O of n? Let's think about it. So this is, the reason I came up with this example is because you need to be aware of other methods or functions that you're calling. So in this case, this algorithm is actually n squared, just like our first example. Now you might be wondering, well, I only see one for loop. Why is this actually O of n squared? So if we look at line 72 here, data.index is actually looking for this value and trying to give us back the index for it. So now, again, you need to be aware of what index is actually doing. So I'm going to just say right here, like index is not a magical method that's going to know like, hey, yeah, this value is an index 99. Like I just know that. No, index is actually going to have to search through your data to find what it's looking for. So this, in effect, is another for loop. Like we can implement this as a for loop and try to find that value. That index is actually doing that kind of behind the scenes. So it's a function that's actually trying to find this item for us, and it's just easier than writing a for loop, but it is still having to go potentially through my entire data to find that value. So again, we have a for loop here, but then inside we're actually running through our data potentially all over again. So this is actually n squared when you combine line 71 and 72. So the key takeaway here is, again, be mindful of the methods or functions that you're calling because they can impact your time complexity. So don't just kind of say, okay, I have one for loop, this is O of n, like I know that, right? No, because you have index, which is also going to be another factor of n. So you have n times n, that's going to be n squared also. So I'm going to just write O of n squared here. All right, hopefully that example made sense. I have one more example for you guys. So let's get to it. All right, so here I have example 3 with a function named example 3. Hopefully it didn't surprise you there with that naming. So this function actually takes an input string. It's actually going to convert that string to a list. So it's a list that I create, depending on those values. And then we're going to go through that list and see how many times we find these letters. In this case, I have an array or a list with CAT in it. We just want to know how many times we encounter those letters. So I have a count variable that just counts up every time we find one of those and return it, return the count at the end of this function. So take a moment here and kind of try to figure out what the O of n time complexity is, and then we'll talk about it in a second. All right, hopefully you guys are at a moment to think about it. And so let's kind of analyze this. So I do have a for loop here. I'm going through my input string. So that's gonna tell me that this is at least O of n. And then I have another for loop that I'm starting on line 106 here. So one thing to keep in mind here is, yes, that I am going through my input size. So in this case, let's say my input string had 10 characters in it. I'm going to run one for loop that goes through the entire string. So it's going to go through 10 elements in this for loop. But then I have a separate for loop that I start on line 106. So just alone here, this is not O of n squared. The reason being is that these for loops aren't nested. So I'm going to run this 10 times, and then I'm going to run this for loop 10 times. Again, we haven't analyzed anything below it, but just looking at these two separate for loops, the one on line 103 and the one on line 106. These are separate for loops that are both going through our input data. So we're going to have 10 elements in our input string and then eventually 10 elements in our data. But these are separate. So like we'll run this 10 times and then we'll run this for loop 10 times also. So that's going to be a total of 20. But again, we're still bounded linearly, meaning if our input size like grew to 100, we're going to run this 200 times, which means we went from 20 to 200, but our input went from 10 to 100. So we're still, proportionally increasing our size equally as our input grows. Hopefully that concept kind of makes sense. So yeah, if they're nested, that's a different thing than if they're separate for loops that kind of complete before the other one begins. All right, but let's move on from line 106. We see a nested for loop here. So again, this is similar to what our example before, where we have a for loop and then we have a nested for loop. So this is going to maybe lead me to believe that this is actually O of n squared also. However, this actually is not O of n squared. So don't fall into a trap where you see, okay, I see two nested for loops, this is O n squared. I know, like, don't automatically jump to conclusions. You got to analyze how the algorithm is actually performing based on your input data. So again, in this case, I have a cat variable that is fixed size, as in this is not going to be growing based on my input here. So if my input, for example, were 100 characters in the string, my cat variable stays constant. That's 3 values. Or I might add a 4th value later, but it's still constant. It's not growing with my based on my input. All right, so in this case, this for loop is a nested for loop, but it's not running over your input data. It's a fixed size. So I know that this is always going to run 3 times for each iteration because cat has 3 elements in it. So this is going to be a fixed size. So this is actually contributing O of 1 to my algorithm. Like again, if I have, 1,000 characters in my string or 1,000,000, this for loop is always just going to be 3 times. Yes, it's going to be run potentially, based on my data. If my data is 10 elements, this for loop will be run 10 times, but the inner for loop will only run 3 times. So it's like, if I do that math, I have 10 times 3, it's going to be 30. Again, that's still scaling linearly. So again, to say that again, if my input were 100, then my inner for loop will run 3 times each time. So it's going to factor up to 300. But as we can see, when we went from 10 to 100, my iterations went from 30 to 300. That's the same factor. So it's proportionally growing with my data. So that's why, again, this does not contribute any added complexity. This is constant time, so O of 1. So I take O of 1 and multiply it by O of n, because I'm actually iterating over my entire data on my outer for loop. So combining those, I get O of n time complexity. All right, so maybe that was a little tricky, but again, I wanted to highlight some caveats with analysis. That is, you got to be mindful of what your algorithm is actually doing. Don't simply just say 2 for loops, that's O of n squared, right? As we saw in our previous example, don't just say I only see 1 for loop, so this is O of n. You got to also make sure what work is being done inside the for loop. You got to know the complexity of that. So in this case, for example 2, line 72 is actually O O of n complexity, and my for loop is O of n. So you multiply those together to get O of n squared. All right, but down here in example 3, our data is only being impacting our algorithm for the outer for loop here, not the inner for loop. And then the for loop that we have above it on line 103 is independent, so it's not going to multiply with this for loop. All right, so in this case, example 3 is actually O of n. All right, so those are some examples. Hopefully you guys kind of can understand how to analyze algorithms, but definitely take some practice. So kind of just get better with it over time. All right. Okay, guys, so I have one more example for all of you, and I think it's the moment that you all have been waiting for. Let's have an algorithm face-off. So in tonight's main event, we have linear search facing off against binary search. And now I know these are both algorithms that we've seen before in past coding challenges. And some of you may have been wondering, you know, linear search is definitely easier to implement. It seems to work for my needs. Why do software developers even bother with binary search? And that's a great question to ask, and hopefully we get some answers from this mashup tonight. All right, so let's get to the main event. So I actually have both of these algorithms coded up here. Let me bring those up. Let me split windows. We can compare them side by side. All right, so here are our contenders for tonight. We have linear search in the left corner. Again, this is an algorithm that we've implemented before. Here, I'm simply going through my data set, grabbing each element, trying to compare it against the item I'm searching for. If I do find it in my data, I'll return true. Otherwise, if I get through my entire data set and don't find it, I'll return false. Then on our left corner, we have binary search. Again, you know, we've implemented this before. I promise you there's no tricks here. This is a basic implementation of binary search. Definitely heftier, as we notice. Linear search is a mere like 4 lines of code, versus binary search is nearly maybe 15, 20 lines of code here. So definitely more logic to it. And maybe, again, that's maybe another reason you're asking, like, you know, why would a developer waste his or her time developing something that's more complicated and spend more time when linear search seems to be, you know, seems to work just fine. And again, this is where complexity analysis comes into play. And we'll kind of see that in our matchup tonight. All right, so these are our contenders. Let's send them off back to their respective corners. Let me bring up my main events implementation. So if you guys are following along here, I'm just going to walk you guys through what I have cleared up here so you understand what's going on. I have my contenders that I import. I also am using a timer. This timer will be keeping track of how long each algorithm takes to achieve its task. Then I create my data. So in this case, I'm going to start off with 10 elements. So this is what this value specifies. I'm going to create 10 elements as a list. I'm going to shuffle it, which I guess doesn't make much of a difference. Binary sort does need to sort it, but that's not actually factored in right now. We can just ignore that for now. Yeah, so we're going to have 10 elements, and basically we're going to search for 10 random elements. My criteria is that the elements may or may not be in the data set. The line I have here on line 18, 20% of the time, the item I'm looking for will not actually be in the data set. Otherwise, it will be in the data set. It's just totally random based on the criteria I set up. And otherwise, we're just going to do a certain number of searches, in this case, 10. Each algorithm is going to run its find operation, trying to find the same item in each time in the same data set. Okay, so that it's equal matchup. So we're going to time it and then aggregate that time in our respective variables, linear time, binary time. And at the end, we're going to compute the average based on the number of searches we did and then multiply by a factor of 1,000 just to get more relevant numbers. All right, so that's our main event. Let's get to the show. Let me bring up my terminal here. There's my terminal. Make that a little higher. All right, so we're starting off with 10 elements that both these algorithms are going to have to search through. So let's run this. I'm going to do Python events, and let's give that a run. All right, so here's our output. Again, this is our average search times. We did 10 searches. So yeah, let's look at our results. So linear time, on average, took 0.00077, I believe these are milliseconds. Don't quote me on that, but we're just using it for comparison's sake. Versus binary search took 0.001179 milliseconds on average. So based on these results, it looks like linear search is our winner here with 10 elements, which is definitely kind of surprising. So, should we just crown linear search the champion here? We shouldn't rush to it. Again, much like a boxing match, that's only round 1. We gotta go through all 12 rounds potentially. So let's actually continue on to the next round. So I'm actually going to increase my total elements in the data set to 100. So again, that's a factor of 10. We went from 10 to 100. And let's see how our contenders fare with 100 elements. All right, so I'm going to run this again with that change. And okay, so we see our output here. Linear search took on average 0.002 milliseconds versus binary search took on average 0.0027 milliseconds. So definitely a closer battle here. Actually, if I actually run this a few times, let me clear my screen, run that a few times, we actually kind of see it's kind of neck and neck. Like, the first time I ran it in this iteration, binary search actually was a bit faster on average. The second time, linear search seemed to be ahead. And then the third time, it was really, really close, actually. As you can see, it's just fractionally different there. So again, it seems like they're neck and neck now with 100 elements. So again, when we only had 10 elements, linear search definitely came out on top. With 100 elements, I'm going to say it's pretty neck and neck. So linear search is still ahead based on the smaller data sets and with 100 data elements. But let's actually extend our data size. So I'm going to make it 1,000. I'm going to clear my screen. All right, so we're actually seeing some different results here now. In this case, linear search took 0.015 milliseconds on average, and binary search took 0.005. So binary search was 3 times quicker than linear search when we had 1,000 elements. Let's actually extend that to 10,000, kind of see how our contenders fare with that. All right, so we're actually seeing even more separation now between linear search and binary search. Again, we're looking for the quickest algorithm here. And in this case, linear search took 0.19 milliseconds on average, whereas binary search took 0.007 milliseconds. So again, that's a factor of nearly, let's say, I don't know, maybe 20, a factor of 20 difference, even more than that, when we had 10,000 elements. Let's actually up our game to 100,000 and see how our competitors do. All right, it's taking a little bit of time there. Oh, I didn't run it. All right, there we go. So, all right, so even more separation here. We have linear search, 5.6 milliseconds on average per search, versus binary search is still under that, 0.017 seconds for the same data. Again, searching for the same item each time. Sorry, both of them are searching for the same item on different iterations. But yeah, so we're seeing even more and more separation here. So in this case, this is like a 500 times difference. Again, the larger we get, we're going to see more separation. So our final matchup, our final round is going to be for 1 million data elements. So let's actually run this and see how long each takes. All right, so it took a bit of time. We see that linear search 51 milliseconds versus binary search. It's still pretty low. It's 0.027 milliseconds. So again, this difference is getting larger and larger with larger data sets. And again, like a million data items isn't that unrealistic for the real world. Like think about large corporations, Amazon's or Google's. A million searches is nothing, right, for Google. So they're probably dealing with tens of millions, maybe hundreds of millions of searches, and just like cutting down the search times can have a dramatic impact depending on how many times you're searching for something. So yeah, based on these results, I think it's pretty clear. Again, with larger data sets, binary search by far is a clear winner here. Yeah, so hopefully you guys can see the big differences, especially when we get larger. Binary search is O of log n versus linear search is O of n complexity. So as our data sets get larger, the separation gets larger and larger and larger. All right, so hope you guys enjoyed our main event. Let's kind of wrap up our lecture here with some key takeaways. All right, so one key takeaway is definitely understand what BigO notation represents. Again, this is something you guys might hear in interviews or software developers talking to one another. Just understand what they mean when they say something like, oh, my algorithm takes O of n squared complexity, or even like memory, my memory complexity is O of n, for example. Just understand the terminology, understand what they're talking about when you hear big O notation. Also, be able to analyze your own code, your algorithmic complexity. Again, we had a few examples. Don't fall into the traps. As I said, like when you see for loops, you still gotta be mindful of what the for loops are actually doing. So normally you can say, like, if you have a for loop over your data, that's gonna be O of n. If you have nested for loops over your data, that's O of n squared. But again, you gotta actually look at what each for loop is doing and make sure that it's actually being impacted by your input size, not some other factor. All right, and the final takeaway I want to leave you guys with is just always be mindful of writing efficient code. Again, this is something you guys will get better with practice, but just understand, like, if you analyze your code and see that you have an O of n squared solution, definitely try to implement optimizations if you can, or maybe refactor your algorithm to have a reduced time complexity. But yeah, so again, just be mindful of it. Again, this is something that we're going to talk about more later, but it's something that all software developers need to be better about, implementing optimizations to improve time efficiency. All right, so I hope you guys enjoyed learning about BigO notation and how it can impact analyzing your code. Thanks a lot, guys.